we can use everything that we've already learned about derivatives to compute all sorts of other indefinite integrals. Remember, an indefinite integral is just another word for a general antiderivative. It's an antiderivative with a plus c at the end. Right? So if we wanted to find the antiderivative of sine, we should be looking for some function that when you take its derivative, you get sine. And we know that sine and cosine are sort of derivatives of each other in a way. So maybe your first guess would be the antiderivative of sine is cosine. Of course, we always have a plus c. The problem is, if we were to take the derivative of this, the derivative of cosine is in fact negative sine, which doesn't match what we have here. We have a positive on the outside here. So to fix that, we need to put a negative here. Right? The derivative of cosine is negative sine, so the derivative of negative cosine would be sine. Right? So when we're going backwards and we're doing antiderivatives, it's sort of the opposite of what we had before. Now the antiderivative of cosine would just be regular old sine of x. Plus c, of course, always plus c, because the derivative of sine is cosine, and the derivative of a constant is nothing. Now what's the antiderivative of e to the x? Well, we know this one, right? Nothing happens when you take the derivative of e to the x. The antiderivative of e to the x is just e to the x, except we always have to add the plus c, because when you take the derivative of this, the c will go away and you'll be left with e to the x. Finally, what's the antiderivative of 1 over x? You might be thinking to yourself, this is the antiderivative of x to the negative 1. Can I just use the power rule for integrals? No, right? We had said the power rule only works when your exponent is not negative 1. So don't use power rule here. Use what we already know about derivatives. We learned back in the last chapter that the derivative of ln of x is 1 over x. Of course, we need to add a plus c because we always do when we're taking indefinite integrals. The only problem is we have to be careful here because 1 over x is defined everywhere. So if we want to say that this is an antiderivative of this, this should also be defined everywhere. So what I'm going to do is put absolute value signs around it just to say this is a function that's defined on all real numbers except for 0, and so its derivative is also 1 over x for all real numbers except for 0. Okay, so using this we can do a few more examples. Let's say we wanted to find the antiderivative of, let's see, where are we? Okay, 3 cosine of x minus 4 sine of x dx, right? This dx, remember, is just saying with respect to x at the end. So let's take it one piece at a time. We know that the antiderivative of cosine is sine. We did that up above. And so the 3 just comes along from the right, and you have 3 sine of x. And we know that the antiderivative of sine is negative cosine. So the antiderivative of negative sine would be positive cosine. And of course, we always put a plus c at the end. We can check our work here, right? We can always check our work. If the antiderivative that we're claiming is 3 sine of x plus 4 cosine of x plus a constant, the derivative of that would be, the derivative of 3 sine is 3 cosine, and the derivative of course 4 cosine is negative 4 sine of x plus c, right? This is just using our regular derivative rules from last chapter. This matches the original function. Oh, no, not plus c. Derivative of c is 0. So this matches our original function here. That's how we know we did it right. Try another example. If we want to take the antiderivative of 3e to the x minus cubed root of x squared plus x to the negative 1, let's first try to rewrite our original function here. Leave 3e to the x alone, that's fine, but rewrite this without the radical sign. If I want to get rid of that radical sign, I'm going to have to change that to a 1/3 exponent. So this is like x squared to the 1/3. And I'm going to rewrite x to the negative 1 as 1 over x, maybe because that might help me remember the antiderivative of this is ln of x. So rewrite it one more time, 3e to the x minus x to the 2/3 power plus 1 over x with respect to x. And now I can finally take the antiderivative. All I've done so far is rewrite this original thing. Now I'm going to actually take the antiderivative. when I take that antiderivative, I can stop writing the integral sign, right? Stop writing that little curvy s thing. And I get the antiderivative of 3e to the x is 3e to the x. The antiderivative of x to the 2/3, let's see, we're going to have to add 1 to the exponent to get our new exponent using the power rule. 2/3 plus 1 is 2/3 plus 3/3, which is 5/3, times 1 over the new exponent, 1 over 5/3, plus finally the derivative, or antiderivative of 1 over x is ln of x. Put absolute values around there so the domains are the same, and then plus c. And if you wanted to rewrite this a little bit nicer, without this 1 over a fraction, you could rewrite it as 3e to the x minus 3/5 x to the 5/3 plus ln of x plus c. So there's your antiderivative. And you can take the derivative of this and check and make sure that you actually get this original function here. Okay, one last example. We've got this whole big function here, right? A polynomial on top over x squared, and you might just be tempted to take the antiderivative of the top and the antiderivative of the bottom, but don't do that, because remember, that's not how derivatives work. If you're taking the derivative of a fraction of a rational function, you wouldn't just do the derivative of the top over the derivative of the bottom. So you can't do antiderivatives that way either. It's not going to work. Instead, what you should do is try to rewrite this first without the fraction. Right? I can rewrite this without a fraction by just dividing each individual term by x squared. Right? So I could rewrite this as, well, what's 5x cubed divided by x squared? It'll cancel out 2 of the factors of x, and I'll just be left with 5x. Plus, what's 2x squared over x squared? 2x squared over x squared, the x's cancel, so it's just 2. Plus, what's 7x squared? I'm sorry, 7x over x squared. Well, one factor of x will cancel in the numerator, but we'll still have 1 below, so we can write that as 7 over x. And then what's negative 2 over x squared? That's just negative 2x to the negative 2 dx. So now that I've rewritten my original function in here, I can use power rule for the first term, power rule for the second term. This is looking like an ln of x antiderivative, and then power rule for the last term. Okay, so going through and applying the power rule and then the ln of x rule here, the antiderivative of 5x would be 5. X needs to increase by 1 here, so it's going to go to x squared, and I put a 1/2 up front, plus 2. All right, this is like an x to the 0 power attached here, so I can add 1 to the exponent and get x to the 1 power times 1 over 1, plus this is like a 7 times 1 over x, and the antiderivative of 1 over x is ln of x. And then finally, minus 2 times the antiderivative of x to the negative 2. We'd have to add 1 to the exponent to get negative 2 plus 1 is negative 1, and multiply by 1 over negative 1 out front. And plus c, always plus c. Simplifying this just a little bit, we get the antiderivative is going to be 5 times 1/2 is 5/2 x squared, plus 2 times 1 is just 2, x to the 1, plus 7 ln of the absolute value of x, minus 2 times negative 1 gives me a positive 2, x to the negative 1 power, and at the end, of course, plus c. You can take the derivative of this and check that you actually end up getting something equivalent to this in the end. It'll look more like this, but it will be equivalent to this. It's kind of wild, right? Looking at a function like this to say that its antiderivative is actually this function with a log in it, right? But that's what we've learned about antiderivatives. The antiderivative of 1 over x is always going to give you an ln of x. Okay, so notice that for all of these functions that we've done, right, anything that we've looked at so far, if it has an antiderivative at all, it actually has infinitely many antiderivatives, because that general antiderivative plus c, that c is just a stand-in for any constant you can think of. Any real number could go there. But if we know the output of the antiderivative for some specific x value, we can actually find a unique antiderivative. So I'm going to give you an example here. Let's say we know that f prime of x is equal to 3x squared minus 2x plus 1. And we know that the original function f, whatever it is, satisfies that f of 1 is equal to 5. We can actually find that unique f of x function. We don't need a general antiderivative here. If that f of 1 is equal to 5, then there's only one f that's going to satisfy this instead of infinitely many, and we can find it. Here's how we do it. Step 1, find the antiderivative, general antiderivative, of that f prime of x function. So I'm going to take the antiderivative of 3x squared minus 2x plus 1 with respect to x, using the rules that we did before. All right, so the antiderivative of 3x squared, well, I need to increase my exponent by 1, so it'll go up to x cubed and multiply by 1/3, minus 2, the antiderivative of x would be x squared times 1/2. And then the antiderivative of 1 would just be x. And then, of course, we have a plus c at the end for now. Simplifying this, 3 times a third is just 1x cubed, minus 2 times a half is just 1x squared, and then plus x plus c. So here's our general antiderivative of f prime of x. Right, we want to figure out what exactly this c value is. So what do we know? Well, we know that f of 1 is equal to 5. And we know that in general, f of x, the antiderivative, is equal to x cubed minus x squared plus x plus c for some c. So if we were to plug 1 into this function, we get 1 cubed minus 1 squared plus 1 plus c for some c, but we also know that f of 1 is equal to 5. And knowing this allows us to solve for c. Right, we have 1 minus 1 plus 1, that just gives us 1 plus c is equal to 5. And subtracting 1 on each side allows us to conclude that c is equal to 4. So the general antiderivative was of this form, but now I've actually solved for that specific c. So in this case, f of x is going to be equal to x cubed minus x squared plus x, and then plus 4. Because we solved for c and found that c was equal to 4. Okay? So once you know the antiderivative evaluated at a particular point, you can find for that unique antiderivative. Let's look at one more example. Suppose f prime of x is this function here, 6x cubed plus 1 over x. And suppose we also know that f of 2 is equal to 1. Let's try to find that antiderivative function f, that specific single antiderivative function. Right? Step 1, we want to find the general antiderivative of the f prime function. So find the antiderivative of 6x cubed plus 1 over x with respect to x. Well, it's going to be easier, just like in the last page, if I divide each term by x to get rid of the fraction. So I have 6x cubed over x would be 6x squared plus 1 over x. So you can write that as x to the negative 1 if you want, or just write it as 1 over x with respect to x. And now actually take that antiderivative, so we can stop writing the integral sign. I'm going to have 6 times x to the third power when I add 1 on the exponent, and then multiply that by 1/3, 1 over the new exponent, plus the antiderivative of 1 over x, which is just ln of x, absolute value of x, plus c, of course. Simplifying this, 6 times 1/3 would be 2x cubed plus ln of x plus c. Right, So f of x is going to be equal to this function for some c. Now step 2 is to actually find c using the fact that they told us up above that f of 2 for our function f is going to be equal to 1. You know that f of 2 is equal to 1. Well, we also know that f of 2 is equal to this function right here evaluated at 2. So 2 times 2 cubed plus the natural log of the absolute value of 2, which is 2, plus c. So I set this equal to 1 because f of 2 is equal to 1 and solve for c. 2 times 2 cubed would be 2 times 8, which is 16, plus ln of 2 plus c is equal to 1. And I'm just solving for c, so I need to subtract 16 on both sides. We get ln of 2 plus c is equal to negative 15, and then I subtract ln of 2 on both sides to get that c is equal to negative 15 minus the natural log of 2. That's not a very nice looking constant, but it is a constant, right? It is an actual constant value. And so I can go back to my f of x and substitute it back in to say that now we know that f of x is equal to 2x cubed plus ln of x plus, instead of c now, I can plug in what I just found. C is equal to negative 15 minus ln of 2. And there's my one specific f of x function.